start. So it's my pleasure to have Jim give a seminar today. This is a joint seminar between the FACS group and the BCS and the RoboStar Centre here in New York. And I think it's one of the first times that we ran one of the FACS seminars here in New York. So hopefully we can do that more often instead of always being in London.
Okay, thank you very much indeed for the introduction, Alvaro. Hello all you local people. Hello everybody online. I see some very old friends who I haven't met up with for a long time, so I won't get into any conversations now, but it was very nice to see your pictures on the Zoom screen. I'm going to talk about verifying system level properties of neural network robotic controllers. And this is joint work with Ziggy Attala and Cavalcanti. And I'll say a bit more about the nature of that joint work in a couple of slides' time. And as Alvaro said, I'm from the RoboStar Centre here in the University of York. And RoboStar Centre is producing technology for producing, designing, verifying, validating robots, especially the software engineering aspects of robotics. So I'll start with an overview of my talk, a short overview, and then I'll give you some motivation behind the work. Then I'll tell you about the RoboStar vision, and I'll discuss how we model ANNs, how we specify ANNs, artificial neural networks, and then I'll draw some conclusions by highlighting what I think our contributions are and where we're going in the future. So here's the overview. I think that verifying artificial intelligence in general, and machine learning in particular, is challenging. So verifying learning-enabled robotic systems is part of that challenge. And I've come to think of it as one of the biggest challenges that faces us as scientists and engineers, but also society. So there are existing techniques and tools for verifying ANNs, but these tend to be component level properties that they're verifying. Not exclusively, there is work on system level properties. So our work is very specific about verifying robotic systems with ANN control components. And we model and verify the entire control software. We take a holistic view, actually, of the robot itself with system level properties. And we focus on a particular kind of neural network, trained, fully connected, ReLU activated neural networks for control. Now, there's nothing specific about the training. We'll come to verifying how you train these networks later on. And the fully connected aspect of it, well, we're focusing on a particular class of ANNs just to get going. And then we'll generalize what we're doing in the future with more exciting activation functions than ReLU, perhaps. So we combine models and verification of the behavior of a robot with the ANN components and models and verifying them and putting the whole thing together. And we combine traditional verification tools with ANN-specific verification tools. And I'll talk about just one of them in this hour's seminar. So we use RoboChart, a domain-specific robot modeling and verification framework. And we have a strategy for automated proof using Isabelle HOL and Marabou, which is the one ANN verification tool that I am going to talk about. So the talk is based on a paper and a thesis. There's the paper. It's written by Ziggy Attala, Anna Cavalcanti, and myself, and it's called Modeling and Verifying Robotic Software that Uses Neural Networks, and it was published at ICTAC last October. It's based on Ziggy's thesis. Anna and I were the joint supervisors, and Ziggy was the hard worker. And his thesis is called Verification of RoboChart Models with Neural Network Components. And that was successfully defended last year. And Dr. Attala now has his PhD. Well, the graduation hasn't happened, but in all but that. So it's very recent work, and I'm pleased to be able to talk about it. So let me give some motivation. Here's a picture. On my computer, I can enlarge this with my trackpad. So I'll have to ask your indulgence, and I'll read it out to you. I went to a factory that makes laboratory robots. And you can just see, if you look in the picture, you can just see a rack where test tubes go for the experiments. And this robot puts very precise amounts of chemicals together to do experiments in those test tubes. Now, the robot has an enclosure around the outside. And I was amused, I suppose, to see this notice on it. And it says, let me read it out for you. It says, robot may suddenly move without warning. Keep door closed when running or when not in use. So the robot's dangerous. But the future of robotics is not in cages. Robots are leaving their cages now. And whenever you have a robot and a human interacting together, you've got a problem with trust. You want to be able to trust the robot, or the property that justifies that trustworthiness requires verification. And so the current approach to software engineering for robots, for engineering the control software, is ad hoc and code-centric. I think that is the state of the art in production. I just come back from a trip to China where I saw robots being produced. And I think I can take a world view of the veracity of this statement. So we're introducing a series of domain-specific modeling languages with tractable mathematical models, with denotational semantics and algebraic semantics and operational semantics based firmly on mathematics. And, well, if we model a robot, we've got to model the hardware platform, we've got to model the environment it finds itself in, we've got to model the control software that makes the robot do what we want in that environment. The hardware model has to have an electrical system, it has to have perhaps a hydraulic system, perhaps it has to have mechanical descriptions of its joints and all these things. So the challenge here is integrated reasoning across all these different facets of a robotic system. And it's a systems engineering problem. The models, of course, are heterogeneous. The control software is discrete, but those aspects of the hardware are all continuous, and certainly the phenomena in the environment are continuous phenomena. And so we have to reason across these heterogeneous models, be able to talk about properties that are true because of several of those models, not because of one individual model. But here in this talk, I'm going to focus on verifying ANNs and not all the other aspects. So I'm going to talk about neural networks for control. So let me give you 4 examples of using a neural network in a robot. And they seem fairly trivial, but I think they put in perspective what we're doing. So the first one is a robot motor, a controller for a robot motor. This is a neural network controller. Suppose there's just a single sensor input to this component. And that single sensor input is telling us about the gradient of the floor as the robot goes forward. And this might be an accelerometer that's giving us this input. So the goal of the control system is to adjust the motor to maintain the robot's speed. So when we're going uphill, the motors go faster because there's more work to do. When you're going downhill, they can ease off a bit. And the idea is to maintain the robot's speed. We need a controller to do that. So here's a little neural network that's going to do it for us. The input layer's just got a single neuron, very simple, and it represents the sensor reading. There's an output layer, again with a single neuron, that converts the gradient to the motor input voltage, And the gradient voltage is somewhere between 0 and 1 volt. And that needs to be scaled and mapped to the motor voltage, which is somewhere between 0 and 6 volts. And so what we do is, of course, we just scale the gradient voltage to get the motor voltage. And we scale it with a factor of 5. And that gets us in the right range. But there's a requirement here, which is that the motor needs a voltage of 1 volt at least to start moving. So what we do is we scale and then we add a bias of 1 volt. And that gives us the right kind of input for the motor. Of course, it would need to be fine-tuned with training data, but this is the idea of what the 2 neurons are doing. And so the scaled and biased neuron output gets converted to an actual voltage signal by a digital to analog converter. Second example, a robot arm. So this robot arm, we've got a neural network controller, and the arm is sorting objects and putting them into different sorting bins according to their weight. Now, this time it's slightly more interesting because there's a hidden layer. So the hidden layer has 2 neurons in it. So 1 layer, 2 neurons, and it captures different features of the input. And in this very simple example, the 2 neurons capture different weight ranges. And this allows them, the network, to make a more accurate sorting decision. So there's one dimension that's given by having more neurons in a particular layer. You can do some more interesting things about a feature of interest in the input. So, slightly more complicated example, the controller for a robot with autonomous navigation. So this robot is going to work out what the steering angle should be in its steerable wheels, based on the distance to the nearest sensed obstacle. So there are 2 hidden layers now. So we've got input, hidden layer 1, hidden layer 2, output. There are 2 hidden layers, and they're computing different features from the input data. So unlike the last example where we had more neurons in a single layer, what these layers are going to do is do more interesting things as you move to the right in the diagram. So hidden layer 1 is responsible for low-level feature distance to the nearest obstacle. So it's getting a sensor, a voltage that's describing something about the distance to an obstacle, and it's going to take that value and turn it into a qualitative understanding of the obstacle. So it's going to identify different distance ranges. The obstacle is near, it's at a medium distance, or it's far away. So it's done something, it's summarized the data for us. But it's a fairly low-level thing. It can recognize changes or gradients in the distance values, but that's really what it's doing. It's extracting simple features from the data about the obstacle's proximity. Now, the hidden layer 2 computes a higher level representation from hidden layer 1's result. So a higher level representation from that low level feature. And so this is mapping the distance to angle ranges. Make a sharp turn. Make a moderate turn, make a slight turn, go straight on. Okay, so now we've decided something about what we're going to do based on the low-level analysis. And so we can identify patterns that need obstacle avoidance or course correction from this neural network. So what's going on here is we're learning perhaps a non-linear mapping between distance and required angle adjustment. So my final example of a neural network controlling a robot has a probabilistic output. So imagine that our robot arm can grasp and manipulate objects of different shapes and sizes and materials. So what we want to do is we want to predict the probability distribution over different grasping strategies or configurations of inputs about the object. So now we can use information about the object from those senses, and we can also use information about the environment. And the input layer is taking as input a 3D point cloud of data. And that might be derived from depth sensors or cameras. And add to that information about the robot's current state, the state of the arm joint angles, and the gripper position, and so on. And then the hidden layers take those inputs and from them extract spatial features and patterns. And then the output layer has multiple neurons, and each represents a different grasping strategy. So if I have these inputs, what's the probability that a top grasp is going to be a better strategy than a pinch grasp? So the strategy is top grasp, side grasp, pinch grasp, and so on and so on and so on. And many strategies we might be able to use. And so the output is the predicted probability for the corresponding grasping strategy. And so what you end up with is a vector of values, and the softmax activation function will turn that vector into a probability distribution by normalizing those scores. So dividing each by the total sum. That's the softmax. So, more motivation. Why should we use neural networks for control? Well, to handle complex and non-linear environments, this is robot control in dynamic, unstructured environments where we can learn complex non-linear mappings from the data. Could use ANNs because of adaptability and generalization. We're talking about new situations not explicitly covered in the training data, operating environments with changing conditions and novel scenarios. The ANN is very good, of course, learning from experience. So continuous training with reinforcement learning to improve behavior, continuously adapt to changing conditions and new tasks. And handling high-dimensional data, process and integrate high-dimensional data from sensors, extract relevant features with different hidden layers. And this is challenging for traditional algorithms, and it's something that's very natural for an ANN. We can use ANNs because of the end-to-end control we get. What's going on here is that the training data maps raw sensor inputs on the left to control outputs. And it enables end-to-end control without feature engineering or state estimation. State estimation, a big problem in robotics. We can use ANNs because we can exploit nice hardware that's very suitable for ANNs. So parallel processing. Real-time control tasks require low latency and high throughput. And we can use GPUs and specialized hardware accelerators. So we can do things very fast. That's a really important reason for using an ANN. And for scalability and modularity. ANNs are naturally modular and scalable. And you can integrate new sensors, control outputs, and task-specific modules without having to completely revise the control system, because the control algorithm doesn't exist. It's just the function that you're computing. So why shouldn't you use neural networks for control? Well, replacing a traditional algorithm with a neural network is quite a challenging task. Why? Because you don't know when you've done it, right? You've got to get it right. It requires very large amounts of training data. The control could be potentially unstable. You've got a new problem to deal with. There are correctness and safety concerns. There are difficulties in interpreting and explaining the learned control policies. And in practice, many robotic systems don't do one or the other. They have a hybrid solution that uses both a traditional algorithm and an ANN. So they use ANNs for specific tasks or modules, like perception and motion planning and low-level control. And then they use traditional controllers to handle higher-level decision-making. So it may be a VDI agent or something. So this higher level is usually task planning and safety-critical operations. And so there's an engineering decision all the time, the choice between when to use a traditional and when to use an ANN controller. And that, of course, depends on specific applications and requirements and constraints and trade-offs. Okay, so that was my motivation. I hope you see why it's an interesting problem. Let me talk a little bit about the RoboStar vision. So we want to work with real robots. So we want to work with real roboticists, real robot engineers. And they have some certain fixed ideas for very good reasons. One of them is to use simulation as their main V&V activity in developing a robot. And they have some very good commercial tools. So we would like our RoboStar platform to make sure it interfaces nicely, plays nicely with commercial tools. People in the industry use practical programming languages, so we have to make sure that we can use practical programming. The validation technique is about testing of simulations and testing of the deployed robot, the deployed code in the real hardware operating in real environments. So we have to make sure that we can generate tests and interact in a way that's familiar with these people, for these people. But we can also add value, and we can add value by using some of our verification tools, by doing certain proofs that are giving results that are simply either too difficult or even impossible to achieve using traditional techniques. And so those, of course, will be model checkers and theorem proofs. And providing evidence of those properties that we can use in assurance cases. Cases for security, for safety, and other critical properties. And we have a significant asset in our centre, which is RoboTool, which is the tool that we use for developing models for robotics and then carrying out the verification and validation that we need to do for those things, and interfacing with simulation tools and generating code and deploying the final robots. And finally, part of our vision is to be application agnostic. We don't apply to this kind of robotic application, but we hope to apply to them all. We hope to be cross-application. And so we have a model-driven engineering approach. Everything's a model, whether it be the software components, control software, the physical robot, the scenarios for the robot, the operational conditions in the real environment for the robot, the interaction with human behavior, and the properties that we want the robotic system to have. All of these are models. They all have mathematical semantics, and all the ones that I've mentioned are different in nature. This really is a heterogeneous collection. But they all have semantics in our meta-semantic framework of UTP, Unifying Theories of Programming. And that's how we can actually do reasoning across the variety of different models that we need, because there's a meta-semantic framework that allows us to understand when a property is impinging on other models and what it means for that property to be true in those other models. So our core notation is RoboChart. And let me give you an example. I'm afraid I can't enlarge the diagram, but what you're seeing there, if you could see it in sufficient detail, is a state chart. There are boxes which are states that have mathematical inscriptions in them, and there are transitions between those states which have mathematical inscriptions on those arcs. So we can tell how the mathematical model evolves in time as a state chart. So that's an example of a controller. And in RoboChart, those controllers have state charts to describe behavior. Those state charts can execute in parallel. You might have several controllers within a single robot, and those controllers execute in parallel, so their models are considered to execute in parallel. We have got a very simple component model that explains, especially when we're developing these things, how different objects in the model relate to each other. And communication is either synchronous or asynchronous. So parallel controllers synchronize with message passing and synchronize on events, and that is synchronous. But a controller and its hardware, the communication is asynchronous, of course. These models are platform independent. They don't depend on particular hardware. And they're describing events and operations, which are the capabilities of the model. And it could be timed, and it could be probabilistic. So how do you derive value from a RoboChart model? Well, if you start with a specification of what you want the system to do as a RoboChart description, one thing you can derive from that is a simulation model. Now that has a different paradigm. Instead of being like a reactive process with lots of operations and events, the simulation model is a cyclic mechanism. It's going around a loop where it does some inputs, does some calculations, does some outputs, and then goes around that loop again. And in fact, the events are translated into interactions with sensors and actuators. So we can derive a simulation model. We can derive simulation code from the simulation model. And that might be for these sorts of commercial simulation tools, Capalia Sim, Gazebo, Drake, and even RT Tester. And then from the simulation code, you can derive the deployment code, the program that actually runs in the real robot at the end of the day. We can do automatic test generation from any of these models. There's a way of describing the operational requirements in a domain-specific language called RoboWorld. And we can do model checking of these models using FDR4, which is a model checker for CSP, and I'll explain why in a moment. And Prism, which is a way of checking probabilistic reactive modules. So these two model checkers you can use directly from RoboTool. And we can do theorem proving. When the state explosion problem gets too big, we can turn to a theorem proof and do some interesting things. And we can write down property specifications in RoboCert, which is a domain-specific language that's very convenient for writing down properties. And there's ongoing work. You're hearing about the neural network work. There's also work on interaction with human beings and on safety cases and several other areas that I haven't listed. So here's a description of the RoboChart modeling stack. And I won't go through this in great detail because I want to focus on neural networks. But if you look at the top left of the picture, you'll see RoboChart mentioned. And there's a module there, which is the kind of basic component that you might be wanting to describe. And each of those modules lives in an architecture. There's a domain-specific language for describing the architecture. And if you go vertically down from that point to the bottom left, you'll see how the things I was talking about before get realized here. You can move from the RoboChart description to the RoboSim description. You can move from there to the simulation code. You can move from there to the deployment code. And the architecture just doesn't have just the RoboChart modules. You can have neural networks. So reading across the top line there, you can have neural networks and a description of operational requirements in RoboWorld and a description of how the interaction with humans is assumed to go. So this is the picture, which is the modeling stack. On another occasion, I'll describe all that in great detail for you. But let me move on and talk about the comprehensive support that RoboStar gives for developing robotics. We start with a description in RoboChart and RoboWorld that gives us a model of what we want to do in what kind of environment. And from that, we can automatically generate a proof model. The pictures that we hope engineers like to draw all have mathematical semantics, and that semantics is in the process algebra CSP, communicating sequential processes. And so that proof model can be generated fully automatically and inserted into a model checker or a theorem prover with some RoboCert properties, and then checked. And if it turns out that the properties aren't valid in that model, instead of going and changing the proof model, we insist that people go back and change the RoboChart model, the RoboWorld model. And eventually you hope this loop terminates and out you pop. And when you do, you can automatically generate a simulation model in RoboSim. Now, From the RoboChart and RoboWorld model, we can automatically generate test cases. And those test cases can be used in a simulator. So one of those real-world simulators, taking the RoboSim model. And those can be checked. And if that's invalid, go all the way back to the beginning and change the RoboChart or the RoboWorld and try again. And eventually this loop will terminate. And when it does, you can automatically generate deployment code. Of course, you want to test that deployment code, and you've got some test cases, but those test cases are for the model. But that can be converted to test cases on the deployed code, and that can be used in system testing. And that can be checked, and if it doesn't pass the test, then you go all the way back to the beginning and you change the specification. And that's the model-oriented approach. And eventually this will terminate, you hope. And when it does, you've got some interesting artifacts. You've got things like the code to run in the robot. You've got proofs that you can use as justification and assurance arguments. You've got test results. You've got assumptions that you've had to make that they're now part of the interface. And you've got restrictions on the environment. And all this information is enough for us to be able to say it's guaranteed trustworthy. So that's the workflow for the support that RoboStar gives. So what about neural networks in RoboChart? Well, they're trained neural networks. They're feed forward. They're fully connected, and they have as activation functions either a linear function or a ReLU function. And as I say, these are temporary restrictions, but we start with RoboTool. We start by constructing from RoboTool, within RoboTool, a RoboChart module. And automatically generated CSP semantics. And then from that CSP semantics, you can automatically generate the unifying theories of programming, UTP semantics that's used for CSP. And that's a well-known semantics, and you can simply translate CSP into that representation. So the CSP semantics is the algebra, the UTP semantics is the underlying denotation semantics, what we want to chew on in one of our theorem proofs. But we can also arrange to have the artificial neural network. If our model is cyclic and memoryless, we can generate an ANN. If it isn't, well, we could do some refinement, or you can go back and change the model until we've got a cyclic memoryless model. And from that, we can obtain the RoboChart description of the ANN, which of course has a CSP semantics, which of course has an underlying UTP semantics. And now we're in a really interesting situation. We have a control problem, right? The control of the robot. And we have two descriptions of how we want to solve that problem. So we have some meaningful redundancy, and that's when you can do verification. You can check one against the other. We can check the UTP description of the ANN against the UTP description of, well, either the control algorithm or the property-based specification of the control algorithm. So that should be refinement, shouldn't it? But actually it's not refinement because the ANN is doing something approximate. It's computing an approximate function. So this is a conformance relation. It's refinement within epsilon. The results that you get are plus or minus epsilon correct. Okay, and you can carry out that conformance check by using Isabelle UTP, which is a version of Isabelle HOL that has the theories of UTP implemented in it. And that might actually require take advantage of a link with the Marabou verification tool. Now, what else can we do? Well, from the neural network, that has CSP semantics. And what we could do is we could generate a Java program that has the same behavior. And we could use the JCSP Java class library for CSP to get code. And then we could use that as a simulation of the ANN And it's rather good because we don't have to make compromises about real values and so on. Well, not as drastic and dramatic as the compromises we have to make with the FDR model check. We can also generate automatically C and C++ code. And we can use that in the simulation. And we can actually compare these two simulations. And then we can do some other formal methods oriented stuff. We can do assertional reasoning with the Java modeling language, JML, write assertions in the code for the simulation and use them to do runtime checking of the runtime verification of the simulation. The C and C++ simulation, of course, we can use that code directly in the commercial simulators like Gazebo, Capelius, Sim, and Drake, and so on. So here's a tiny example. One of the examples from Ziggy's thesis, a Segway. You've seen these things. You stand on them. They've got two wheels and a handle at the top, and it's one of the first. The control law is an inverted pendulum. It's one of the first exercises in a MathWorks course where you're developing some PID controllers and so on. So it's an inverted pendulum. There's two motors, one on each wheel, and it's continuously putting torque on the wheel in order to keep the device upright. And the particular little example we've got is a miniature version of the Segway. And when you power it on, it learns how to stay upright. It trains itself, and then it could be used to deliver I don't know, a piece of paper down the corridor or something. And on the right, you have a diagram that's describing at a kind of architectural level. The controller on the left is describing the interface to the controller, and on the right, it's describing the hardware. And if you could read the tiny script, you'd see there are 3 gyroscopes here, and something that's recording the angle of the Segway, and then a couple of interfaces to the motors on the wheels. So what does the language look like? The RoboChart language with ANNs embedded in it? Well, a RoboChart module consists of state machines, but also ANN components. And the ANN components have a meta model and some well-formedness conditions. And the state machines can be used to provide us with a data-rich process algebraic semantics. I've been talking about the semantics in CSP, but if there's state there, then Circus is very useful. And if we add the ANN meta model and demonstrate the well-formedness conditions, then we have a Circus model of the ANN and conventional state machine description in RoboChart. And then from the Circus semantics, we can derive 3 things. A JCSP version, we can encode it as machine-readable CSP, and we can encode it in UTP. And then each of these can be analyzed using OpenJML for the JCSP, using FDR4 for the CSPN, and using Isabelle UTP for the UTP, but maybe with Marabou. So that's what the language looks like and why we're using it in the kind of workflow based on the structure of the language. Okay, so let me tell you about how we model ANNs. Here's a diagram that explains what I'm about to talk about. Suppose you have a RoboChart description of a controller, and that's iterative. We can use semantics of CSP and the laws of UTP to produce a description of what that controller is doing. And that's a reactor contract. And I'll explain that in a few moments. And that describes the controller, but with application-specific events. Now, we can do the same thing for the ANN. We can take a RoboChart ANN call and, well, first of all, sequentialize it. Within a layer, the nodes can fire in any order, right? So there's an awful lot of interleavings. And for the memoryless ANNs I'm talking about here, we can sequentialize it without affecting the behavior. So we sequentialize it to make our life easier, and that gives us a sequential CSP process. And from that, we can derive a reactive contract pattern. So now we have two contracts, one for the traditional controller and one for the ANN controller. And of course, we can compare them. The second, the ANN, is a different structure. It's describing a deterministic function on a trace-based specification, whereas the traditional one is describing things with application-specific events. But traces lie at the bottom of both of those models. So we can prove conformance, we hope. Conformance within epsilon, and we can, in that conformance proof, we can generate some reachability conditions, and from those we can strengthen those and bound those in various ways to get verification conditions, and we can discharge these with Isabelle UTP, or Marabou, or a bit of both. So what do these models of ANNs look like? Well, each neuron is just a concurrent process. Processes communicate through channels, representing the weights between neurons, and the synchronization and communication is just CSP primitives. And this formalizes information flow and computation within the neural network. And the parallel and distributed nature of CSP gives us the ability to execute multiple neurons simultaneously. And we can do formal verification of these models, and we know how to do that. We have FDR4, which is a successful model checker, providing your models are small enough. But we also have an implementation of the semantics of CSP in Isabelle UTP. So we can do verification there. And we can check for convergence, stability, robustness, and specific properties that we're interested in. And, well, everything here is compositional. CSP is nicely compositional. We could scale the analysis and verification of larger ANNs. And of course, this is an active research area worldwide, searching for formal foundations for ANNs. So we have a data flow architecture for these ANNs. And we're modeling an ANN as a recurrent data flow network with transforming buffer nodes. And I'm using buffer in the technical sense of a FIFO data structure that's free from deadlock, free from divergence. It has the FIFO property for things that go through it. If it isn't full, it won't refuse to input. If it has content, it won't refuse to output. And now I'm talking about transforming buffers. So they don't just let things flow through them, they actually do something to the data as it goes through. So implement this model in CSP and analyze it in the tools I've talked about. Now, because those transformations, multiplied by a weight and adding a bias, because they're total, that ensures the network's totality. You compose total functions, you get a total function. The data flow architecture ensures network deadlock freedom. It also ensures divergence freedom. And the architecture and the transformations ensure determinism. So we get a lot of properties from the pattern that we're using. So here's an example. Suppose we have one input layer. We have n hidden layers, and we have one output layer. So the layers are indexed between 0 and layer number, where layer number is n plus 2. And the nodes are connected with communication channels. So layer L, node n, like a matrix, we're indexing it, layer L, node n, has inputs on layer res, that's short for layer result, from the previous layer, that's L minus 1, to this node. And that node outputs on layer res, layer result, from layer L, from node n. So it comes in on L minus 1 and goes out on L. So now consider a very small example. One input, one hidden, and one output layer. Node. So there are 4 channels. There's the input channel from the outside world. There are 2 hidden nodes. There are 2 channels, one from each hidden node to the output node, and then there's an output from the output node. So 1, 2, 3, 4 channels. There are 3 processes, 2 hidden nodes, node 1, 1, node 1, 2, and 1 output node, node 2, 1. Right? Layer node is the index. Where's the input node? Well, there's no material behavior in the input node, so we don't bother to model it. And what the process is doing is inputting and outputting. What the network is doing is inputting and outputting. What the nodes are doing is inputting, doing some stuff, and outputting. So the node is recurrent, and some of my descriptions, I leave that implicit, a bit like an action system. So here's the output node. It has this behavior. It inputs from the 2 hidden nodes. Okay, I've chosen to input from node 2 first and then node 1. So I get X from node 2 and Y from node 1. The question mark in the CSP denotes input. So having got X and Y, which is the previous layer's values, I now output on the output channel, that's layer res 2, 1. I output X plus Y multiplied by the weight and add to the bias, and then take the ReLU. Spit that out and then terminate. And that's what the output node is doing. ReLU, by the way, is an activation function. ReLU of X is the max of X and 0. So it's cutting off the negative values. That's its activation. And by the way, weight and bias should be indexed by the layer and the node. And I've chosen just to simplify all my descriptions and leave that implicit. Imagine that these are alphabetized by L and M. So here's our CSP model of an ANN with 1 input node, 2 hidden nodes, and 1 output node. It's the 1, 1, 1 layers. And so you see the input goes simultaneously to the hidden nodes. And that's what fires them all together, because they get an implicit synchronization from that one-to-many channel. So that fires things off. And so each of the hidden nodes takes its input and outputs this weighted biased sum. It's a little affine transformation of the input. And then it terminates. So they don't do anything interesting. And you saw what the output node did already. And so look, there are indeed only 4 input channels. Only 4 communication channels. The input channel, the 2 hidden channels, and the output channel. 4. And there are only 3 nodes, because there's no interesting behavior in the input node. Okay, so that was a CSP model for a very simple one. Now I'm going to risk something and show you the model for an arbitrary ANN with an arbitrary number of layers and an arbitrary number of nodes in each layer. So hang on to your hats. So here's the definition of an ANN. It's some very complicated process, semicolon, a recursive call. Okay, so this is tail recursion, it's just iteration. So forget about the semicolon ANN at the end. Okay, now what's the main connective of the very complicated process? It's that backslash hidden event. No, it's not. It's the triangle end. The triangle in CSP is an interrupt. So the very complicated process can be interrupted by an end signal that shuts it down, because afterwards it skips and terminates. So what is it that could be interrupted? That's the process to the left of it. And you see the hiding operator, that backslash, hide the hidden events. So the internals, those channels in the diagram that are not the input and not the output at the extremities of the neural network. So everything else is being hidden. Now, you now see 2 processes in parallel. Hidden layers in parallel with some gobbledygook, in parallel with output layer. So the hidden layers in parallel with the output layer. So the output layer is different from the hidden layers. It has a different structure, right? Slightly different structure. And the hidden layers and the output layer communicate on which channel? Well, it's the output from the hidden layers. Now that can't be layer res dot layer number, because that's the overall output. It's the one just before that. So it's layer res dot layer number minus 1. So that's how they're interacting. So what are the hidden events? Well, I told you it's the whole alphabet except for the end event, the incoming inputs from the sensors and the outgoing outputs to the actuators, right? It's everything else. Okay, so what are the hidden layers? Well, it's a whole load of layers in parallel. So here you see an indexed parallel composition. What's it indexed over? By the indexes of all the hidden layers. So that's not index 0, because that's the input layer. It's not index layer number, that's the output layer. It's all the other ones. It's 1 up to layer number -1. And then the actual things that are being put, the actual layers are described by hidden layer, without the S on the end. And the little bit of gobbledygook in front of that tells you what the interface is to each layer. And it's the channel coming in, that's channel L-1, and it's the channel going out, that's channel L. So now we can look at hidden layer, and that has some parameters. It has the layer number, and it has the number of nodes in that layer, that's S, and it has the number of inputs, that's input size. And what we have here is a parallel composition of all those nodes. So I ranges over all the node index. It's 1 up to S. And the nodes are described by the process node. And you see the interface to that is the channel coming in, because there's going to be a different channel going out. You'll see that in a second. So here's the node. And this is made of two things. The interleaving of some stuff in parallel with a collator. And what the collator is doing is picking up all the inputs, weighting them all. And when it's got the weighted sum, it then adds the bias and spits it out. So that's what the collator is doing. It's collating the inputs and producing the output. So the node in process is what we have to look at next. Now, we're actually down to a proper process, not some composition using CSP's funny operators. So what does node LNI do? So L is the layer number, N is the node within that layer, and I is the ith input transition coming in, the ith input channel coming in. So for those three parameters, we want to pick up the input. Now that's on L-1, that's incoming. That's incoming to, it's the ith one that's incoming, and it'll give us a value, and that'll be X. So let's keep that X, let's multiply it by the weight, and let's spit it out on this channel you haven't seen before called node out, which is going to go to the collator. Right? So spit it out on node out, and it's LNI of that value, and then terminate. So what does the collator do? Well, it's just a recursive function. Ln input size. So layer L, node N, with input size number of inputs coming in. And so collator of that is just in this recursive definition. It's this final line, CLN input size 0. So these three parameters are just as they were before, and 0 is the sum. And then there's two recursive definitions. You see that input size is being used as a variant, and we're counting down to 0. And so when we count down to 0, we bottom out, and there's no more recursion. Now, if I is not 0, then we have a sum, and so we suck in on that node in input, the ith input, call it X, and add it to the sum. And don't forget to decrease the variant. And eventually this will bottom out and you'll get down to 0. And then when you're down to 0, you can take that sum. Remember, these weights could all be different. So we've got that sum. We can now add the bias to it, take the value of it, and spit it out. Spit it out to the next layer. In this definition, L and N don't change at all. If you found that slightly confusing, they don't change at all. They could have been abstracted. And then finally, there's just one last definition. which is the output layer, which is very similar to the hidden layer, except we don't have some of the structure. So what the output layer is doing is having enough nodes, right, enough output nodes. So layer size gives us the number of nodes, and layer size of layer number is the number of nodes in the output layer. So we have enough nodes, and we take each of those nodes, and we get the idea. Wow, so that was the formal definition in CSP of an arbitrary neural network. Now I need just to get a little bit of a move on. So let me talk about Marabou. This is an SMT-based neural network verification tool from Stanford University and Galois. And it gives formal guarantees about properties and outputs. One thing it can do for you is prove robustness properties, so it can verify behavior with respect to input perturbations and adversarial attacks. It can determine the maximum perturbation for unchanged outputs with respect to specified thresholds. It can determine the output range given possible output. It gives possible output values for given input ranges. It can do input-output verification, check if input patterns always lead to specific output patterns, including checking if certain output classes are never produced for certain sets of inputs. It can prove safety properties. It can ensure that the output doesn't exceed certain thresholds. It can ensure certain inputs never lead to unsafe outputs. And it can be used as part of end-to-end verification, which of course is what we're doing here with RoboStar. We're going to exploit some of these properties. So, am I okay to continue for another 5 or 6 minutes? Sorry. So, specifying ANNs. What I've done so far is I've given you some motivation. I've talked about RoboStar and the workflow and so on. I've discussed the nature of the CSP model that we use. What I'm now going to do is show you how we specify what an ANN does. And we do that using a reactive contract from UTP. So this is an extension, a contract extension for the semantics of state-rich CSP processes. It provides a rich set of algebraic laws for process verification. And every circus program, so every state-based CSP program, has a reactive contract. So there are some observational variables in these contracts. There's a state before and a state after, which is a mapping from variable names to values. There are flags to say when you've started the program and when it's reached a stable state. There's a record of the events that are being recorded by the process. A special derived observation called TT dash, which is just the difference between TR dash and TR. This is the contribution made by this process. Stuff may have been done before, right? There's a couple of flags to show that when we're quiescent, a reactive process, of course, is one that pauses in a stable state for interaction with the environment. And so if OK dash is true and wait dash is true, then this is paused. There's refusal sets. In fact, ref is never used. It's only ever ref dash that is used here. And these are things that the process won't do next. So you see this is a state-based version of CSP, and would be a suitable semantics for a language like Alchemy. So a reactive contract then looks like this. Not sure you can see with all the noise and the syntax, but there's 3 parts to it: P, Q, and R. P is the precondition, R is the postcondition, and it's that kind of assumption commitment contract we're talking about. But there's a 3rd part, the middle part, Q, which is the what's called the Perry condition. That's the things that must be true before starting and after starting and before terminating, the Perry condition. So the semantics are OK and P implies OK dash and and then a conditional, if weight dash, then Q, else R. So let me read that in English. If we initiate the process in a state where the precondition is true, then we will reach a stable state. And if we've terminated, the post-condition will be true. If we're waiting for interaction with the environment, the peri-condition will be true. So this is an assumption commitment contract for reactive processes. You can talk about those stable states during the execution process before it gets to the end. So P is the precondition, R is the post-condition, Q is the peri-condition, and their relations on various combinations of the variables. So we have a simple pattern for reactive contracts for use with ANNs. And this pattern I call these two predicates, peri and post. In the paper, you'll see a calligraphic E and a capital phi. I keep getting confused with arcane notation, so I call them peri and post. So peri is a predicate on two variables, T and E, and post on T. So the peri condition says we've seen the event trace T, and we're not refusing any of the events in E. So E is an acceptance set. And there's the meaning. Peri TE is TT dash, that's what this process has done, is the whole of T. And the refusal set dashed, intersected with E, is empty. And the post condition just says that T has been observed, right? And you've seen this notation, I'm not sure I explained it before, but the open face curly brackets describes a set of events. And they're all the events that are communicable on the channel C. So all events that are extensions of the name C. And so here's our conformance relation. I think in my eagerness, I've omitted one of the slides for the contract, but the contract should say never diverge, so precondition true, and then peri-condition. If we're in the input phase, we're not refusing the next input. If we've completed the input phase, we're not refusing the output. And then the post condition should say you did all the inputs and you output this value. So that's the contract. And now you can write down a function as a constraint on those three values. So the conformance relation is refinement within epsilon. So Q conforms within epsilon to P, means there's a sequence of events S and a set of events A, and those are the approximations that we're going to use. And so TT, which is going to be the trace that's been formed by Q, TT is a sequence approximation within epsilon of S. And that means if you take corresponding pairs in the two sequences, they are the same modulo E, the same plus or minus E. And then alpha P minus ref dash, that's the acceptance set version of the refusal set, is a set approximation plus or minus epsilon of A. And now we have a refinement statement that says P with S instead of TT, and the acceptance alpha P minus A instead of ref dash is refined by Q. So there you have S is an approximation of traces, A is an approximation of acceptances, and only outputs are being approximated. So there's our conformance relation. And now I just need to give a couple of slides on conclusions. So I think our contributions in this work are, first of all, a method for robotic software with reliable white box ANN components. Deductive guarantees on the behaviour of system level properties. Platform independent models for validation, simulation, and verification. A meta model for trained feed-forward fully connected ANNs of any size or shape. And general extensible formal representation of ReLU ANNs. And validation with FGR4 and simulation with JCSP, and a reactive contract theory that enables verification inside Isabelle UTP. So the ANN property proof method is based on refinement that's hidden inside conformance. And that hiding inside conformance is dealing with numerical instability of ANNs and provides a worst case error bound, plus or minus epsilon, and allows for substitutability. We can substitute the ANN that comes out of this workflow for a RoboChart controller, either the algorithm or the property-based specification of it, with a guaranteed error bound. And we have an example case study, this inverted pendulum PID controller. We need many more case studies. And we're able to translate the reactive contract to multiple input-output reachability properties for verification using Marabou. And this is an integrated approach to reasoning about ANNs using a variety of techniques. We can do simulation and proof using Java and standard commercial tools, and proof in Isabelle and Marabou. Final slide. We need more case studies. We need some challenge problems which are bigger than case studies. We need to look at timed models and probabilistic models and simulation models, and we haven't dealt with perception at all. And that's the end of the talk. Thank you.
Thank you, Jim. We have some time for questions, so the questions in the room or online, just, yeah, Susan?
Very nice, as always.
Oh,
Thank you very much. Really enjoyed that. I'm interested in recurrent neural networks. How many years am I going to have to wait until this has been extended to recurrent neural networks, not just feedforward?
Well, as you know, I retire in September.
So quite soon after that, you mean?
Quite soon after that, I'll be able to devote myself full time to your question. It's difficult, isn't it, predicting what happens in the future? But of course, there are many places where we really need to go, where we want to go. This is an absolutely incredibly intellectually interesting area, and there's a lot of work to do. We have colleagues in Brazil, of course, and Denmark and China, and so who are going to help us with this work. And I think it's really, really exciting to build on the work that Ziggy has founded here. Thank you for the question. Ziggy.
I actually wanted to answer that question.
Okay.
To address more to Jim's. So, okay, so in terms of the actual CSP model for recurrent neural, so I've thought about looked into this, and in terms of, and then with the utility direction contract for that, it's not that bad. However, in terms of in terms of getting a real verification, an automated verification engine is the problem for recurrent neural networks. That's where specific solvers are still quite far. There are some coming out, but still quite far away. There's other dimensions of neural network that I kind of want to go into as well. But in terms of the model, it's not about the verification is very difficult. Yeah, that's it.
Yes.
Yeah, absolutely. Yeah.
Any other questions? Online people, do you have questions? Just unmute yourselves and. Oh.
Hello, this is Tim Denver. Hi, Jim. Long time no see.
Hi, Tim. How you doing?
On slide 10, you used the phrase low latency, and my first thought was, what is latency in this context? Low latency suggests rapid or at least timely response. What would that be right?
It is exactly right, yes. You want the neural network to be up to the task of being able to control the robot in real time. So it needs to be able to react very, very fast. So it is exactly that, yes.
Thank you.
Thank you, Tim.
Anyone else?
Hi, Tim. So very nice presentation. Thank you. I guess my question is there a way to move beyond verification to more towards synthesis? So I would be interested not only to verify that it's neural networks, but actually to start from high level governance of the system, since we are talking about system level, and somehow derive at least the right neural activations, maybe functions, maybe even architecture.
I think that's a very
That would be very exciting.
I think that's a very good question. Just to make sure the people online heard it in its entirety, the question was about moving away from verification to synthesis. Can we synthesize the right ANN for the control problem with all the weights and biases in place? So synthesize it rather than train it and verify it. So one interesting approach to verifying training is to use a Ziggy approach. And that is a synthetic approach. That's an approach to synthesis. And that neural network training and Ziggy, they just look so much alike, right? And so you could do that with a correct by construction approach to the ANN, and that would be your synthesis problem.
No, that would be very interesting.
Yeah.
What was that name?
CEGAR, CEGAR, counter-example guided abstraction refinement. So in the software world, you might build a model, and you've got some properties, and you build a model, and you want to transition a diagram for your system, and so you put all the transitions that are possible into the diagram. So it's the full graph, and then you consider each transition and you say, does that have my properties? Does that have the right kind of properties? And if it does, you keep it. If you don't, you prune it. And so you might have 100,000 or 1 million transitions, but each invocation of the theorem proof or the model checker is using ground terms, because you've got a specific transition in mind. So instead of verifying one big theorem, you're verifying 1 million little theorems, but they should all be automatic. And so this is the other big contribution that Annie made. And it's a popular technique. I saw another question.
I was just talking. Yeah, so I actually wanted to kind of add to this discussion that you said, because I've been thinking about this as well in the future. The question could be as well. So as well as what Jim what Jim was saying about that, you could also, if you wanted to abstract the details of the training method. What I think is interesting is making place instead of an arbitrary software model with multiplication multiple architectures of neural networks, where you get this from how the non-determinism works in your model, or from how the discrete variables, or how the actual hybrid state is set up. And either one of those, you could then generate architectures and then go and try to prove conformance, as we've shown through that, which is another kind of way of looking at it, which means you could abstractly use any training process. And then the cigar could be kind of an addition, a different way of doing it for certain different sorts of models. For doing that, they could both be different directions to explore. Just wanted to kind of add that. But yeah, something I think is very interesting for the future. But yeah.
Thank you, Ziggy. I suppose an intermediate stepping stone would be to go for some sort of neural network repair. So you don't go for the full-blown synthesis, but if the verification fails, you may attempt to somehow repair the neural network.
That's not very, that's not very interesting.
Sort of middle ground between verification and synthesis.
The second one. So you said when you finally get your proof that the corrected stats includes some environmental constraints that have to hold in order for proof. How those is there any way of sort of writing those in a way that you could actually make sure the environment followed those constraints? If I'm thinking in a controlled environment, it might be relatively easy, but if you've kind of got autonomous vehicles in a quite uncontrolled environment, what kind of things are you going to be able to say in court? Oh, well, sorry, the environment it was too cloudy that day and it shouldn't have been used, or something like that. What kind of environmental constraints do you end up having to specify?
I don't have enough experience to be able to give you examples of it. However, suppose your robot is inside a nuclear reactor, and the constraint is don't wander too close to the edge of the pile because you'll fall off. Right, you're in danger of falling off. And there are some environmental constraints there about the kind of obstacles and the guardrails and so on that you could actually look to see if they're in place.
Yeah.
But I think it's a really good question. It's a really good question. There are two sorts of preconditions, aren't there? There's the precondition about how you would like the world to be, and there are preconditions about how the world is. I remember in Jonathan's specification of microprocessors, there are preconditions like the register must be 64-bit as part of the precondition. Well, did you make it like that or not? Right. So that's how the world is. And there are other preconditions about how we'd like them to be. Now, some of these environmental constraints are about one of those things and not the other, and some of the other ones are the other way around. And so you can check to make sure both of them are the case before you loop. Now, I think that's the kind of thing that people use for spacecraft digital twins and so on, to be able to do experiments and to find out those things. Hey guys, that turned out to be a really bad idea. So don't do what we just suggested. We just discovered that there's a problem.
We have a question online.
Yeah.
Ready? We can't hear you.
That's
He's typing his question in, I think.
Yeah, okay, he's back to the question. Thank you.
So, the question is, what is Isabelle's role in the verification? So Isabelle's role in the verification is to prove some properties, but also to help organize the verification, help organize the workflow, and to be able to say when things could be farmed out to tools like Marabou. The second part of the question is, are the nodes modelled in Isabelle and the network? Are they modelled in Isabelle? Well, they're modelled in CSP. They're modelled in RoboStar, in RoboChart that has the CSP semantics. So they're modelled in notations that Isabelle understands. You say, does that not pose problems for scaling? Of course it does. Of course it does. If you have many nodes, and they all have, you know, some different structure, some different characteristic, that means you can't take them all as being like one another and prove generic properties about them, then of course that would be the case. I honestly don't have enough experience about reasoning about significant neural networks yet to be able to say why I believe that these are going to be scalable. There are good results that come out of Marabou about scaling up, but you know, there are neural networks and neural networks. Dealing with 10 hidden layers of 10 nodes in each is pretty scary, but it's not as scary as reasoning about a large language model, where you've got several hundred hidden layers with several hundred nodes in each, and that is scary. And I think we're a few years away, just to follow up on Susan's point, we're a few years away from being able to say very much about that. But do we need to? It may be that there are small versions of the neural network trying to get out, and that's where compositionality comes in, proving things about parts of the neural network. And you may be able to partition the problem in various ways, but compositionality comes to the rescue. So once again, the search for compositionality is going to dominate the research agenda, I think. Thank you for the question.
Yeah, sorry. I just wanted to add a little bit as well to answer that question. Might seem strange, but like because initially, so we do have the node representation inside Isabelle, but we don't actually perform proper reasoning on each node, even though each node exists for a proper reason. And the reason why is because we more use those to generate a constraint on the output, a constraint on the input and the output spaces of the neural network, to then go and use that that kind of relation constraint to go and act. That's what we actually go and prove, not in each kind of node separately. We just use that as an interim almost to get to that the vector space theory, honestly. We use it to get that, which we then go and do verification with. So yeah, just to kind of add that as well to the discussion. But yeah.
Thanks, Ziggy. Thank you.
Any more questions? Okay. I had one that kind of was related to Rado's question, I think. Would it make sense to use the work that's being done on test generation to produce the trainings data for the A&M?
That's a very interesting point. It would make sense. It would make sense, yes.
Thank you.
There's an interesting paper that I heard just before the pandemic. I was in Shanghai, and I went to a big workshop on verifying AI. And there was a paper there that talked about doing coverage testing for neural networks. And they had a lot of evidence that the sorts of problems that you get in software that are helped by doing coverage testing are not the sort of problems you get in neural networks. And so the way that you look at the space, if you're using software engineering techniques, testing techniques, might just be mistaken. You're looking at the wrong sort of thing. Now, I could produce that reference at some point. It's a very interesting observation, which shows that empirical software engineering is really important in this area. We don't know enough about what mistakes people are making in large neural networks. What kind, and you want testing techniques and verification techniques to rule out whole classes of errors that you don't know what the classes of errors are. So I think that's an interesting point.
Thank you. If there are no more questions, I think we can conclude the talk. Thank you again, Jen, for the very interesting talk.